Alright friends, welcome back. In this video I'd like to go ahead and move on here in Chapter 7 by taking a look at Section 7.2 of your textbook, and in this video I want to basically ask and answer a simple question. And as weird as this is going to sound, that question is this: do matrices behave in the same way that numbers behave? Okay, so we learned in the last video that a matrix is basically just an arrangement of numbers into rows and columns. Typically we use them to model stuff like real-world data and that kind of thing. But in this video, what I want to do is I want to put our mathematician hats on a little bit and investigate, are these arrangements of numbers something that we can look at as its own object? And does this object behave in the exact same way as an object that we're already familiar with, which is the entire concept of a number itself? So again, I know that that idea kind of seems a little bit weird and meta, but that's exactly what we want to investigate here in this video. So specifically, we're going to take a look at what it means for two matrices to be equal to each other. We're going to take a look at what it means for two matrices to be added or subtracted from each other. We're also going to have a brief discussion about how to multiply with matrices, and then we'll take a couple of looks at examples of matrices involving stuff with the calculator, and then we'll call it a video, okay? So let's have a look first at equality, right? So remember, what it means for two numbers to be equal is that they have the same value. So for example, if you have a number like square root of 9, that is the same number as 3 because both of those numbers have the same value. They both represent the fact that I've got 3 is my result, right? Well, it's the same idea for a matrix, but remember that because matrices are arrangements of numbers, we have to make sure that they have the same arrangement of their numbers first. And by that I mean that they need to have the same dimensions, okay? So that's the first thing to check for. If you want two matrices to be equal, they both have to have the same number of rows and the same number of columns. And then after that, this next part plays very nicely with your intuition. It's just going to mean that every single corresponding entry of both matrices is going to be equal to each other in value, right? So you can see that down here where I have a number like simply the square root of 4 being in the same entry as the number 2. Those have the same value, so we have a green light here. Same thing with a number like 1/2 having the same value as 0.5. That checks out. But you'll see here in this next example that these are not equal matrices because while you can see here that a couple of corresponding entries match up, they do not have the same dimensions, right? So this first one, you may remember from the last video, is a 3 by 2 matrix, and this next one is a 2 by 2 matrix. And so those dimensions, of course, don't match, and so these are not equal matrices. And so what we can start to do is take a look at a couple of examples that involve this idea of matrices being equal to each other. And so this first example is so straightforward that I went ahead and just did it for us already here. We can blatantly see here that x is in the same entry as -13 and y is in the same entry as 12. So since they're in the same corresponding entries as each other, we can just go ahead and say that those are equal. And after checking to make sure that my matrices have the same dimension, which checks out here, right? These are both square matrices, 2 by 2. We can go ahead and confidently say that x is equal to -13, y is equal to 12. In this next example here, let's just check real quick that they have the same dimensions. It looks like these are both square matrices. These are both 3 by 3 matrices. So that's important to always check first. And then after that, we can go ahead and start matching up corresponding entries here. Now, before we start doing that, one of the things that I want you to notice is that we can go ahead and pick which pair of entries we want to go ahead and match up here, right? So for example, you may notice that in the top left entry, it says x plus 2 in this first matrix, and then in the top left entry, the corresponding entry, it says 2x plus 6 in this next matrix here. You can feel free to go ahead and solve this problem by setting those entries equal and then getting the correct answer. That is a completely legit way of doing it. But if you look around a little bit more, you might notice that you have another pair of corresponding entries that can let you get x in a little bit of an easier way. So specifically, you may notice that you've got 2x here, and then its corresponding entry in the other matrix is -8. So if you can find a pair of entries that correspond to each other that are a little bit easier to set equal to each other and to solve, then I might encourage you to do that just for the sake of making life easy for you. Okay, you'll get the same answer either way. But I think we'll blatantly see here that x is going to be equal to -4, so that's pretty easy. And then we might just look for a pair of y entries here that are corresponding, so we could set those equal. So again, you may have noticed that you've got y plus 2 and 11. You could feel free to set those equal and solve if you like, but I think a little bit easier would be to notice that we've got 2y here and we've got 18. again, it's not wrong to pick one over the other, but it's just for the sake of making life as easy as possible. We could simply divide both sides by 2 on that and see that y is going to be equal to 9. So again, when we say that two matrices are equal to each other, that is something that I feel like is going to play very nice with your intuition. Just check that they have the same dimension and that corresponding entries match up. Those are going to be equal in value. Adding and subtracting matrices is something else that's going to play very nice with your intuition because, again, all we just need to make sure that we have is that they have the same order, and then we just need to make sure to go through and add all the corresponding entries of both matrices or subtract all the corresponding entries of both matrices, right? So a couple of worked out examples here. You notice that in this first example, I am just simply taking a 2 by 2 matrix and adding it to another 2 by 2 matrix. Those have the same dimensions, so we are good to go. We have the green light to go ahead and add these up, which you can see the work for here. We're basically, again, just adding up all the corresponding entries of both matrices and then writing the result in that last matrix there. So I feel like that's pretty straightforward. The next example down, again, the reason that we're not able to add these is because they don't have the same dimensions. So while this first matrix is a 2 by 2, this next matrix here is a 2 by 1, and so we cannot correspond or match up entries, and so we are not able to add these together. So our conclusion would just simply be that this is going to be an undefined sum of matrices. The next couple of examples I've already gone ahead and worked out here as well. You guys can go ahead and pause the screen here and check to make sure that these work out as well. Again, you're checking to make sure that they have the same order, and then after that, you're just adding or subtracting the entries in corresponding positions, and then writing the result in that same corresponding position in a new matrix that you call either your sum or your difference. We can now go ahead and start to define multiplication, and instead of just skipping straight to taking a matrix times a matrix, I want to take a quick pit stop at taking a simple number times a matrix. And when you have that sort of problem, that number that we multiply times the matrix, we're going to give a special name. We're going to call that a scalar, okay? And so this is due to what matrices actually represent whenever you move on to higher level mathematics courses or physics courses, where matrices can start to represent stuff like vectors and higher order objects in these upper level classes here. So we call it a scalar, much like in your geometry class where you had a scale factor that you multiplied times all the sides of, say, a triangle, and it blew the triangle up to be bigger or shrunk the triangle down to be smaller. It's the same idea here. We're just taking this constant of -2 or the scalar of -2, and we're just multiplying it times all the corresponding entries of our matrix here to get the resulting entries of the matrix that I've gone ahead and boxed here. Again, this is something else that is going to play very nicely with your intuition, something that's very, very easy to do. As I go ahead and move on here, the only thing that I want to stress is that you just need to pay attention to what it is you're being asked to find, right? So, for example, here they're asking you to find 4 times a. That just simply means take the number 4, the scalar 4, and multiply it times all the corresponding entries of a, and then write those new entries in their corresponding positions, and then that'll be your new matrix. This next one is saying to take that 4a that you just ended up with and then subtract off the matrix b, and so that's exactly what you just see me doing, right? For example, if I take 4, which is the upper top left-hand entry, and I subtract off the corresponding one, which would be 2 on matrix b, then of course I get that result of 2, and you just do that for the same you do that same thing for all of the corresponding entries in those two matrices. So again, I've already gone ahead and worked those out just for the sake of time. I feel like that's a pretty straightforward idea. Next here, again, some more expressions involving matrices. The only thing that I want to stress here, you can see those screenshots of the calculator, is that you can be using the calculator to do all this stuff, right? So we talked about in the last video how you input a matrix into the TI-84. After you input those matrices, you can go ahead and start to do simple operations with them, just like you see in these screenshots. We can add those together, we can subtract them from each other, we can go ahead and take scalar multiples and then do various different expressions involving them. So that's something that the TI-84 can do all for you, again, just assuming that you go and you type in those correctly, so make sure to catch the 7.1 video for more information about that. This next slide here is just a slide that just confirms for us that so far with the operations that we've talked about, so namely that is matrices being equal, adding and subtracting matrices, and then multiplying matrices times a scalar, this slide right here is just basically listing all the different properties that we can say are true in all cases whenever you're adding matrices or whatever, right? So just kind of go through these really quickly. Number one, that's your commutative property of addition, right? If you take a matrix A plus B, that's the same as taking matrix B plus A, so that follows our intuition. The second one there, that's your associative property of addition when it comes to matrices. So you can group together matrices first and add those first before bringing the third one into the fold. Number 3, any sort of lowercase letter you see in these properties, that represents a scalar. Any sort of capital letter you see, that represents a matrix, okay? And so that third one down is just your associative property for scalars. The fourth one down, that's your identity property, right? So that just is saying that if you take a matrix times the number 1, you get the same matrix back. That's why we call it the identity. The fifth one down, that is your distributive property for a scalar across the sum of 2 matrices. And then the sixth one down, that is distributing in a matrix into the sum of 2 scalars, right? So again, these are all things that we would expect to be true, and these are all actually things that you can go through and prove if you really want to. But again, just pointing these out as standard different operations that we can go ahead and do with matrices. So here in example 5, I've already done this example here as well. This is just to point out that those properties do in fact work. And what you see me doing here is you see that I have a sum of matrices that I'm taking times the scalar of 3. And so the first thing that I'm going to do here, of course, is I'm going to go ahead and distribute this 3 to both matrices. And when I say distribute that 3 to both matrices, I mean we're just going to take the number 3 and we're going to multiply it times each of the entries that are in these 2 matrices before we add them together, which is what you see me doing in that first step. And then I go ahead and successfully add them there as I get my final result there in that last step. Now, it turns out that when you want to multiply a matrix times a matrix, it's going to get a little bit more complicated. Again, and that's due to what matrices actually represent whenever you move on to higher level mathematics courses, physics courses, higher level economics courses, basically any sort of application that matrices have involved themselves with. Multiplication is going to have to be defined in a special way. And I'm not going to get too deep into why we define matrix multiplication in this way. I'm just going to go ahead and demonstrate to you what that's going to look like, okay? I know that it looks like a mess of symbols here, but a couple of things that we need to kind of say before we move on, right? So it turns out that you don't even have the green light to multiply 2 matrices unless their dimensions are in a particular relationship with each other, okay? And that relationship is going to be the following, right? So let's say your first matrix has dimensions of m by n, right? So that means m columns and let me rephrase that. That means m rows and n columns, okay? That sort of matrix you can only multiply times a matrix with these dimensions, right? So an n by, say, p matrix where you have n rows and p columns, okay? What you're looking for here is the number of columns in your first matrix is exactly equal to the number of rows in your second matrix, okay? If those don't match up, then you do not have the green light to multiply matrices in the first place. So that's something that I always want you to go through and check, is that the number of columns in your first matrix matches the number of rows in your second matrix. The reason for that is because we need to define matrix multiplication in a particular way by matching up corresponding entries. And we need to go ahead and make sure that the number of columns matches the number of rows because of how we define this here. So basically the idea of what you're looking at, I know that this looks like a big mess, but all that we're saying here is to get what you have here in the first entry of your product, all we did is we just took all of the entries in the first row of A and we multiplied them times all of the entries in the first column of B. That's why we need all the rows and columns to match up there, right? And then as we move on, we just go ahead and do all the different combinations of pairing a row from A with a column from B, okay? So while that first entry is the first row of A and the first column of B, I might just go ahead and represent that here by just saying the row, you know what, I'm not even going to introduce more symbolism here because I think we have enough of that on the page, I dare say, right? But again, what if you wanted to get the entry that is in this this one right here, right? So that is your second column, first entry, right? Well, that would be simply taking your first row of A times the second column of B, okay? This third entry of your product, we get that simply by taking the second row of A times the first column of B, and then finally that last entry of your product here, this one right here, this is what we get by multiplying the second row times the second column, right? So you can see here that it's basically just all the different combinations of a row from A times a column from B, and we just arrange them in a particular order, okay? What we're going to do here is we're going to multiply corresponding entries and then just add up all the results after doing each of the entries from the rows and columns there, right? So I just want to go ahead and briefly demonstrate that process just once by hand, and then throughout the rest of the video, you'll see that I've already done a lot of those examples for you in the calculator and that kind of thing. So let's just take a look at example 6 here. It just says simply find A times B. I have my matrices A and B listed out here, and the very first thing that we should check for is to see if their dimensions are in that particular relationship that allows us to multiply these in the first place, right? So just checking this real quick, it looks like A is a 2 by 3 matrix. Checking B, it looks like this is a 3 by 2 matrix, and we can see here that we do have the green light because, again, the number of columns in matrix A is going to match the number of rows in matrix B, and so that gives us the green light to go ahead and multiply these together. So I'll say that down here, the matrix A times the matrix B. We're going to go ahead and write this out, okay? So what that's going to equal is basically what we have here as our leftover dimensions, right? So we are going to be left over here with a 2 by 2 matrix, or a square matrix, okay? And so let's go ahead and figure out what that's going to look like here. So we're going to go ahead and do this by taking the first row of A and multiplying all of those entries times their corresponding entry in column B. Okay, so we're just going to go ahead and write this out here really quickly, right? So the first entry of the first row of A is a -1. We're going to multiply that times the first entry of the first column of B, and that here, of course, is -6. Okay, I know that that result ends up being a +6, but we're not quite done here because we're just going to need to add that result to all the different products of the entries that are in the ones that I've circled up here. So we're going to move on to the second entry of the first row of A, that is 2. We're going to multiply that times the second entry of the first column of B, that's -2. And we're going to take that result and add that to doing the last ones, right? So that is going to be -6 times 1. That's the last entry of the first row of A times the last entry of the first column of B, okay? And believe it or not, that is going to be the first entry of this matrix here. So that would have to be something that you go ahead and reach for a calculator in order to go ahead and evaluate here, or you could just go ahead and do it mentally. So I might just go ahead and do that here, right? So -1 times -6, that's just simply +6. 2 times -2 is going to be -4, and -6 times 1, of course, is just simply -6 here. So after adding all those results up, we could see here that the entry is just simply going to turn out to be a -4 for us, and that is going to be that right there, okay? So moving right along here, we're just going to go ahead and continue by taking the first row of A, and now we're going to go ahead and multiply it times the second column of B, and that's going to be in the exact same way that we did the first one, all right? So we're going to set this up, so that'll be -1 times 4, plus 2 times 3, plus -6 times -4, and then just using some mental math to go ahead and add up all those results here. This will be -4, this will be +6, and this will be +24, and so adding up all those results there, I believe what you're going to get there is +26 as your entry. Okay, moving right along here, we're just going to go ahead and do all the other combinations. So we'll move on to the second row of A, which is going to be this one right here. We're now going to go ahead and match that up with the first column of B, multiply all those entries in the way that we just discussed, and then write out what the result would look like. So that'll be 3 times -6 plus -1 times -2 plus 4 times 1. And then just doing the math on that, right? So this will be right here -18. This will be +2. And this will be +4. Okay, so adding up all those results there, I believe you're going to get -12. So that's pretty good. And then finally, we're going to do the last combination of a row from A and a column from B, which would be to say the second row from A and the second column from B. Okay, and so that will be the following. That'll be 3 times 4 plus -1 times 3 plus 4 times -4. All right. And so we'll go ahead and say here that that's going to be 12, this is going to be -3, and this is going to be -16. Adding up all those results here real quickly, I believe that is going to give us -7, and that is going to be our final result for the product of two matrices. So I know that that is a very, very tedious process, but hopefully you were able to see the pattern there. Again, we're just doing all the combinations of a row from A, times a column from B, and then just adding up all of those multiplied entries, right? Now, one of the things that I want to share with you here is that this is something that you can go ahead and do in the calculator really easily. There's a quick snapshot of what the result is, and that, again, that's assuming that you're able to go in and actually plug in what the matrix A is and then separately what the matrix B is. You can go ahead and plug that into the TI-84, and it'll go ahead and multiply those matrices for you, doing all this work so that you can check to make sure that you got the answer correct, okay? Throughout the rest of the video here, I just want to take a look at a couple more examples here. In example 7, it just says find the product of A, B, if possible. Well, let's just make sure that we have the green light, right? So A, B looks like a square matrix. That is a 3 by 3. But if you look at matrix B, it looks like that is a 2 by 3. And we specifically needed these dimensions to be in that special relationship that we talked about. Namely, the number of rows in A is going to need to match the number of columns in B. And we see here that these are numbers that do not match at all. So what that means is that we do not have the green light to go ahead and multiply these two matrices together. So I'll say here A times B is undefined. So always something very important to be able to do is to figure out what the dimensions of the matrices are that you're working with, and that'll give you the green light to do all the different things that we've discussed. Okay? In this example, what I want to go ahead and just simply demonstrate here is the fact that we do not have a commutative property of multiplication when it comes to multiplying matrices together. Okay, so for example, here I've got these two matrices, A and B. You can see that I've plugged them into the calculator, and I've done that order, right? I've done first A times B, and then I reversed that order and then did B times A. It's just by virtue of the fact of how we went through and defined matrix multiplication that it turns out that we get two different matrices here whenever we do these. And so what that's going to mean in general, and this will work for any matrices, right, is that if you were to take this order, A times B, in general, that is not going to be equal to B times A, okay? And so that is one of the differences between matrices and numbers themselves. This will be one of the ways that matrices behave differently than numbers behave, right? Because if you had two numbers, like maybe say simply 2 times 6, then we know that that is equal to 6 times 2 because these both have the same value. They're both equal to 12. So that checks out. However, we are not able to say that the values of these matrices match up because you can see there, according to the calculator, that they, of course, have different values. And so this is one of those properties of matrices that we're going to have to keep in mind, is that matrix multiplication is not commutative. Here are some properties of matrix multiplication that always do work, though, right? So that first property is going to say that if you're multiplying 3 matrices, you do have an associative property of multiplying, which means that you can group together 2 matrices and multiply those first before bringing the third one into the fold. The second one down that has a distributed property of matrix multiplication, that works out fine. Actually, number 3 says the exact same thing, but just in the reverse order there. And then number 4, again, that lowercase letter c, that is a scalar. So if you were to multiply a scalar times a product of 2 matrices, then you can go ahead and look at that as like more of an associative property where maybe you just take that scalar times a first, or maybe you take it times b first, and then multiply your matrices together. So again, these are the different properties of matrix multiplication here. One of the other things that I feel like we take for granted a lot in mathematics is this idea of an identity, right? So when it comes to just straight up numbers, we do coin this term of there being a multiplicative identity, right? If you had a number like maybe say 3, if I wanted to multiply that 3 times something without changing the value of it, I would just multiply it times the multiplicative identity and get my 3 back. And we all know what that number is. Of course, that is the number 1. So we call the number 1 the multiplicative identity in the world of numbers, right? We also have an additive identity. If I wanted to take that number 3 and instead add some number to get that identity of 3 back, then of course we know what this number is, right? In our number system, that would simply be the number 0. So we have this idea of a multiplicative identity, and we have an additive identity when it comes to numbers. And so since we're asking that question, you know, do matrices behave in the same way as numbers, this is another thing to check, okay? And it turns out that there is such a thing as an identity matrix for multiplication, but it has to be defined in a certain way. So you'll notice here that it is an n by n matrix, so it's always going to be a square matrix. And if you take a look at the pattern here in the general definition, you'll notice that it has that column of 1s that we were looking for whenever we were talking about row echelon form and reduced row echelon form, right? So basically you have a diagonal of 1s there, and then every single other entry in your matrix is going to be a 0. That is your identity when it comes to matrices here, okay? And it turns out that they follow most of the same properties as your multiplicative and your additive identity. Getting my words tripped up. These have the same properties as your multiplicative and your additive identities when it comes to numbers here as well. So there's a quick snapshot of how that would work out. Again, here is your identity right here. This is your square matrix, your 2 by 2 that we're multiplying times that first matrix to get its identity back, and the reverse direction also works. So it turns out that whenever we're dealing with the identity, we do get this nice commutative property with matrix multiplication. So that's something good to point out. The last example that I want to focus on here in this video is example number 9, where we're actually taking these matrices and we're actually applying it to a situation. So again, one of the basic concepts here and uses for matrices in the real world is to help us just model data and also to model those relationships between quantities like we saw in the last video with all of our linear multivariable equations, right? So I'll let you go ahead and pause the screen here. All I did as work is concerned on this one is I just went ahead and typed in the matrix E and the matrix C into the calculator, the TID4, and I just went through and multiplied them. The whole idea here is now that we're just going to have to go through and interpret these results within the context of the problem. So when we do that, of course, we see here that we get $2,130 as the amount of money for Team A, and then we get $2,448 as the amount of money for Team B. Okay, so again, I'll let you go ahead and pause the screen there and read through that problem on your own. Again, I know that matrix multiplication is a little bit of a tedious calculation to have to perform, but that is the way that we're going to have to define matrix multiplication whenever we are taking a look at that situation, right? So again, the basic question in this video was, do matrices behave in the same way that numbers behave? The answer is, yeah, for the most part, except when it comes to multiplying two matrices together. That's when we have to go ahead and define that special case. So I hope this video has been helpful to you. Please let me know if you have any questions whatsoever. That's all I have for this one. Thank you very much for your attention, and I'll speak to you in the next one.